We're going to have a look at our second application of differential calculus, which is sketching a function by evaluating the nature of stationary points. Okay, stationary points are defined when the gradient of a function is equal to 0. So this can be done in a few steps. When we're sketching a curve or when we are trying to evaluate the nature of stationary points, we need to find the derivative of a function. That is step number 1. Step number 2 is to identify the x values where this gradient is equal to 0. In other words, that means let the derivative function equal 0. Once we've found those x points, we want to find the coordinate points on that function. So we substitute those x values into our original function to determine the coordinates of these stationary points. And then we've got to investigate, is this a maximum, is this a minimum, or is this a point of inflection? In other words, what is the nature of these stationary points? Let's have a look at how we do this. So I've got a function here. Step 1 is to find the derivative. So here we have found the derivative function, and that's step number 1. Step number 2 is to let the derivative function equal 0. Okay, this will find these stationary points. Okay, I've just factored out a half from my quadratic expression there. I can simplify and solve this out by dividing by half. 0 divided by half is just 0, so I just get x squared. So I've got 2 stationary points here, when x is equal to -6 and when x is equal to 2. Now I need to identify the coordinates of these stationary points. So just as a reminder, we've got our function 1/6 x cubed plus x squared minus 6x, and we've got our derivative function, which is a half x squared plus 2x minus 6. And so I want to find the corresponding y values on my original function. So that is what I'm going to do. I'm going to have to use this guy here. So we found out the corresponding y value would be 36 at the point x being equal to -6. Let's consider it when we've got x being equal to 2. So here, just a little recap of my working. What have I done? I have found the derivative, and then I've let the derivative equal 0. The reason why I've done this is because I'm interested in the points that have got a gradient of 0, those flat points. Those are going to be maximum points, they're going to be minimum points, or they're going to be points of inflection. Then what I've done is I've found the coordinates of these stationary points. I've got -6/36 and 2 -20/3. Okay, now I need to investigate, well, are these points maximums, are they minimums, or are they points of inflection? Because having a look at my working out, I don't know yet. Okay, and so we're going to use a test called the first derivative test, which is essentially, we're going to consider when x is equal to -6, I want to know, is it a maximum, is it a minimum, or is it a point of inflection? I'm going to use the first derivative test. What I'm going to do is I'm just going to investigate the behavior of the function to the left and to the right of the point. So I'm going to consider the point when x is equal to -7 and the point when x is equal to -5, and I'm going to have a look at what is the gradient doing at these points. Okay, and the way I can do this is I write a gradient table up, where I've got my x value and my slope. And so I'm going to have -7, -6, -5, and I know that the slope at -6 is flat, so I'm going to indicate that with a flat line. I want to know what is happening to this function at the point x being equal to -7. Again, because this working out is just so long, I'm going to remind myself, this is my function. And so in order to figure out what the gradient is doing, I need to evaluate the corresponding y value of those exponents on the gradient function. That's going to tell me the slope of the original guy, and we're going to do that. So the derivative function of -7, we're going to have a half inside of -7 squared plus 2 inside of -7 minus 6. Clean this up, that's going to be 49 over 2 minus 14 minus 6. 49 on 2, that's 24 and a half. Subtract 20, that's going to be a positive number. That's all I care about. It's going to be positive. I don't care what the value is, because this implies that my slope is increasing. I've got an increasing slope if that's a positive number, and I can denote that with an increasing line on my gradient function. I'm then going to have a look a little bit to the right at the point -5. Well, half times by -5 squared plus 2, so -5 minus 6. I have 25 on 2, that's about 12 and a half, minus 10 minus 6. So 12 and a half minus 16 is going to give me a negative number. Okay, and this implies that I've got a downward slope. If I've got a negative number, a negative y value coming out of that x point, the slope is going down. So I've got a negative slope, and I can denote that in my gradient table with a downward slope. And so if my gradient was increasing, then it was flat, then it was decreasing, that implies that I've got a maximum point. So I say, therefore the coordinate of -6, 36, is a maximum. It's a maximum point. So that was for x being equal to -6. Let's have a look at x being equal to 2. Okay, so again, I'm going to draw up my gradient table where I've got my x points and my slopes. And I'm going to consider the point, that's shocking. I'm going to consider the points when x is 1, when x is 2, and when x is 3. And I know the slope at the point x being equal to 2 is flat. I already know that because I've determined that. Now I need to work out what is the gradient doing at these other x points. What's the corresponding y value of the derivative function? So half 1 squared. Okay, I'm going to have a half plus 2 minus 6. That's a negative number. It's a negative number there. And that implies I've got a downward slope. So I've gone down, then I'm flat. Now I'm going to have a look at y being equal to, y prime being equal to 3. So half 3 squared plus 2 outside of 3 minus 6. That's going to give me 9 divided by 2 is about, it's 4.5. So about 4.5 plus 6 minus 6, that's a positive number. And that would imply that the gradient is increasing. So I was decreasing, then flat, then increasing. Therefore, this point here, so therefore 2 and it was negative 20 on 3, is a minimum. It is a minimum point. And so just a quick review here of what we've done. We have used the first derivative test to determine the nature of these points, and we have found that this guy here was a maximum by investigating the left and the right, and this guy here is a minimum by investigating to the left and the right. Last step here is to put it all together onto a sketch. Okay, so that's step number 5, is a sketch. And in order to do our sketch, we need to reason some long-term behavior. So our function was, oh, that wasn't in cube there. Our function was a cubic function where we noticed that a is positive, therefore it's a cubic. It's a cubic with a being positive. Therefore, as x goes to infinity, y goes to infinity. That's the long-term behavior. What's going to happen as those points approach infinity, and as x goes to negative infinity, y also goes to negative infinity. I noticed that I've also got a y-intercept of 0. Okay, because this value at the end here, plus 0, that's y-intercept. I don't have a value there. So I'm just going to piece all of this together on my sketch. Okay, so just piecing it together, I know that my two dots there that I've labeled, they're maximum and minimum points, so that's the highest point and the lowest point, I guess, of those functions, not considering the long-term behavior. And it's going to go down, and it's going to pass through this y-intercept and kind of hit down here, and then have this point as a maximum, and then shoot up, and then the arrows indicate that it's going to go in that direction, forever. And I'm just going to label. My graph, and that's it.